Welcome back, Deep Divers. Today, we're going to be taking a look at indeterminacy.
Oh, this is a fun one.
I know, it's a little bit of a brain twister, this one.
Yeah.
So we're going to be kind of going over randomness, all kinds of randomness.
All the way from, like, the stuff we think we kind of know.
Right.
To the, like, super bizarre, we have no idea what's going on kind of randomness.
Yeah. So we're going to start with what we think we know, which is still pretty bizarre.
Right.
So to start us off, how do we really define true randomness?
Well, I mean, it's kind of like, you know, in the normal world, we think about random as like
rolling a die or something.
Yeah, or like shuffling cards or whatever.
Yeah, rolling a coin.
But in a scientific sense, you know, true randomness has some very specific criteria.
So, like, what would some of those be?
So, for example, you know, if you're tracking the movement of a single particle, like just one tiny little thing, for its motion to be considered truly random, the best predictor of where it's going is where it is right now. So it doesn't matter how much data you have, you can't, like, plot its course and figure out where it's going.
So it's like that toddler, you know, who's had way too much sugar.
Oh, yeah.
And they're just, like, bouncing off the walls.
Yeah, exactly. But the thing is, with true randomness,
right,
there is an order to the chaos, right?
Yeah.
So truly random motion exhibits, like, consistent variability over time.
Okay.
And the really freaky thing is you can magnify it as much as you want, so like 1,000,000 times.
Oh, wow.
And it's still going to be random at that level.
Oh, that's trippy.
Yeah, so it's like the universe is fractal, and at every scale there's just this
unpredictability built in.
Yeah.
Wow. So is there anything that we can actually, like, see in real life?
Well, yeah, there is. I mean, it's not
like
perfect true randomness, but it gives us, like, a taste.
Okay.
And that's something called Brownian motion.
Brownian motion.
Yeah. Have you ever seen, like, dust particles in a sunbeam?
Oh, yeah.
They're, like, kind of just, like, randomly moving around.
It's like they're having a rave in there. They're just like...
Yeah.
Just, like, going crazy.
So what's happening there is those dust particles are constantly being bombarded by photons of light.
Oh, okay.
And that's transferring energy to them, causing them to collide with each other and with the air molecules around them. And each of those little collisions is totally random and unpredictable.
So it's not just air currents, it's light itself. It's like...
Yeah, light is...
fueling this dance party.
It's fueling the mosh pit, yeah.
That's so cool. So does that, like, how does that affect us? Like, how does this random jiggling affect anything important?
Well, it actually affects a lot, especially at, like, the molecular level.
Oh, really?
Like, in our bodies.
Okay.
So, for example, things like the connections between nerve cells, like where they form, are actually influenced by Brownian motion. The clustering of receptors that help your muscles function.
Oh, wow.
That's affected by Brownian motion.
Okay.
And even scarier, like the formation of those beta amyloid plaques in Alzheimer's disease.
So this tiny little jiggling is contributing to, like, these major things.
Yeah.
Wow, that's crazy.
Yeah, it's a really fundamental process that affects, like, all sorts of biological systems.
So I guess, like, even from, like, the very beginning, like when a cell divides.
Oh, yeah.
There's got to be some element of randomness to it.
Absolutely. So, you know, when a fertilized egg divides, the way things get distributed, like the mitochondria, which is like the powerhouse of the cell.
Yeah.
It's not perfectly even.
There's an element of randomness to it. And guess what? Brownian motion plays a role in that.
So we're not just, like, these perfectly, like, symmetrical beings. There's this element of chance from the start.
Yeah. And it's not just our genes dictating everything, right? It's like there's this element of chance right from the get-go. That's amazing.
Yeah.
So this random jiggling, it's not just in our bodies, right? Like, does this randomness have any impact on, like, how animals behave?
Oh, yeah, totally. In fact, random movement can actually be a really good strategy for survival.
Okay.
Like, especially in environments where resources are scarce.
Okay.
So, for example, have you ever heard of a levee walk?
Levee walk.
Yeah.
That sounds like a new dance move.
It kind of is. Like, imagine a fish searching for plankton, right? It's not like following a set path. It's kind of randomly moving around.
Oh, okay.
But with these occasional long jumps. And it turns out this kind of random exploration, it's way more efficient than, like, a systematic search.
Oh, that's interesting.
Yeah.
So it's better to just kind of like go with the flow.
In some cases, yeah.
Wow.
So it's not just fish, though. Like, even things like killer whales,
Oh, wow.
hunting for seals.
Okay.
They exhibit these levee walk patterns.
That's wild.
Yeah. And even like white blood cells hunting down pathogens in your body, they do levee walks too.
So this randomness, it's not just a quirk of the universe. It's like,
yeah, it's like a tool.
it's an advantage.
An evolutionary advantage.
Wow. Okay, so I'm sensing we've gone as far as we can go in the world we know.
Yeah.
So I think it's time to dive into a world
Should get even weirder.
a little bit weirder, yeah. We're gonna take a look at the quantum world.
Quantum indeterminacy. Here we come.
I'm ready.
Buckle up.
All right, we'll be back in just a minute to take a look at this strange world. Okay, so we've looked at how randomness affects the world we can see.
Right.
But now it's time to get microscopic.
Yeah. To zoom in, like way down.
Way down to the quantum level.
Yeah, to the realm of quantum indeterminacy.
I'm ready.
All right, well, get ready for one of the most mind-boggling ideas in quantum mechanics.
Lay it on me.
It's called wave-particle duality.
Wave-particle duality. Okay, so what does that even mean? Like, how can something be both a wave and a particle? Those are like totally opposite things.
Yeah, I mean, it doesn't make any sense in our everyday world, right?
Oh,
like,
wow.
a wave, it's spread out, like an ocean wave or a sound wave.
Yeah, it's like all over the place.
Yeah. A particle is like in one spot, like a grain of sand or, an electron. But in the quantum world, things get fuzzy.
So are you saying that like tiny particles, they can just switch between being a wave and a particle?
Yeah.
Like depending on their mood?
It's even stranger than that.
No,
they're not switching. They're both at the same time.
Both at the same time. So they're like a wave and a particle all at once.
Yeah. It's like they're defying the rules we're used to.
That's wild. Okay, so how do we even know that? Like, what kind of experiment could possibly show us that?
So there's this classic experiment called the double slit experiment.
Oh, slit, okay.
Imagine you've got, like, a beam of electrons, and you fire them at a barrier with two tiny slits in it.
Okay.
And behind the barrier, there's a screen that detects where the electrons land.
Okay, so if electrons are just particles, you'd expect to see them, like, hitting the screen in two spots, right? Like where the two slits are.
Exactly. Like, if you were firing bullets through two holes in a wall, you'd see two clusters of bullet holes.
Yeah.
But that's not what happens with electrons.
Oh, really?
When we do this experiment, we see an interference pattern.
An interference pattern?
Like the kind of pattern you'd see with waves, like water waves, overlapping.
So are you saying the electrons are, like, interfering with themselves?
Yeah. It's like each electron is going through both slits at the same time.
What? That's impossible.
That's what's so crazy about the quantum world. It's like the electron is exploring all possible paths at once.
It's like a multitasking electron.
Exactly. But then when it hits the screen, it acts like a particle again.
So it's like wave, 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 and then particle.
And here's the really weird part.
Oh, there's more.
If you try to measure which slit the electron goes through,
Okay.
like if you put a detector at one of the slits,
Yeah.
the interference pattern goes away. It's like the electron knows you're watching.
Okay. So it's like if we're not looking, it's a wave, and if we are looking, it's a particle.
Yeah, the active observation changes the outcome.
That's so trippy. It's like the universe is playing tricks on us.
Yeah, it's a big mystery in quantum mechanics.
Wow. Okay, so how does this wave-particle duality tie into, like, the randomness we were talking about earlier?
Well, the fact that particles can act like waves, it introduces a lot of uncertainty.
Uncertainty, okay.
Like, remember how we were talking about position and momentum?
Yeah, momentum, like how fast something's moving, right?
That's a little bit more than that. It's like how much oomph it has.
Oof. Yeah.
But in the quantum world, because things can be waves, it gets really hard to know both the position and the momentum.
So it's like, it's blurry.
Yeah.
We can't really pin it down.
And it's not just that our instruments aren't good enough. It's like a fundamental limit.
A fundamental limit, okay.
And that's where Heisenberg's uncertainty principle comes in.
Heisenberg's uncertainty principle, yeah, I've heard of that.
So what that principle says is you can't know both the position and momentum of a particle with perfect accuracy.
Okay.
The more you know about one, the less you know about the other.
So it's like a trade-off.
Yeah. It's
Yeah.
like the universe is saying you can't know everything.
Yeah, that's pretty deep.
And even Einstein struggled with this.
Really?
Yeah, he thought there had to be some hidden variables, something we were missing.
Okay.
But it seems like this uncertainty is just a fundamental part of reality.
Okay, so even if we had, like, the most perfect measuring device ever, we'd still run into this limit.
Exactly. It's baked into the universe. It's like the cosmic speed limit.
The cosmic speed limit. I like that.
And what that means is the universe isn't deterministic. We can't predict the future perfectly.
Because there's always this element of
Randomness.
randomness. Yeah, wow.
Yeah. So even at the smallest level, the universe is full of surprises.
Okay, so we've got particles acting like waves. We've got this uncertainty principle. I have a feeling there's more, right?
Oh, yeah, we're just getting warmed up. Get ready for entanglement.
Entanglement, I've heard that's where things get really spooky.
Spooky action at a distance.
All right, let's do it. Let's get spooky. All right, so we've covered a lot of ground here. Like we started with, the randomness we see in our daily lives.
Yeah, the familiar stuff.
Right, and then we dove headfirst into the quantum world.
Where things get really wild.
Yeah, with particles acting like waves and that whole uncertainty thing.
Heisenberg's uncertainty principle, yeah.
Right, but now we're going to tackle what's been called spooky action at a distance.
Entanglement.
Entanglement, yeah. So is it really as spooky as it sounds?
Oh, it's definitely one of the strangest things in quantum mechanics.
Okay, so what exactly is it?
So the basic idea is that two particles can be linked together. In a way that no matter how far apart they are, if you do something to one, it instantly affects the other.
Instantly. Like faster than the speed of light.
Yeah, that's the really weird part.
Okay, so like how is that even possible? Like isn't that breaking some kind of like universal law?
It seems to violate our classical ideas about, cause and effect and how information can travel.
So like if I had two entangled particles and I like flipped one upside down, the other one like across the universe would instantly flip too.
That's the basic idea.
That's just insane.
It's like they're connected by an invisible thread no matter how far apart they are.
Okay, but how do we know that's real? Like how can we even test that?
Well, there have been lots of experiments over the years,
Right.
and they keep confirming entanglement.
Like what kind of experiments?
Well, one experiment involved entangling two photons and then separating them by almost 900 miles.
900 miles.
Yeah, they used fiber optic cables and even satellites.
Wow.
And they measured the polarization of the photons.
Okay, and what they found was the measurements were correlated, even though the photons were super far apart.
So they were like influencing each other instantly?
Yeah, it's like they knew what the other one was doing.
That's wild. So even Einstein, with all his genius, couldn't explain this.
Well, he wasn't a big fan of entanglement.
Really?
He called it spooky action at a distance.
Yeah, I can see why.
He thought there must be some hidden variables, some explanation we were missing.
Okay.
But so far, all the experiments support the idea that entanglement is real.
So it's like the universe is even weirder than we thought.
Yeah, it seems that way.
Okay, so we've got particles that can be in two places at once, particles that can tunnel through walls, and now particles that can communicate faster than light.
It's a lot to wrap your head around.
It is, but is there any practical use for entanglement?
Oh, yeah, definitely. Scientists are working on using it for things like quantum computing.
Quantum computing, okay.
Which could be way faster than our current computers.
Right.
And quantum cryptography. So
Yeah.
like super secure communication.
Exactly, and even teleportation.
Teleportation. Like Star Trek teleportation.
Well, not exactly like that, but it's a step in that direction.
Wow, that's amazing. So I guess the big question is, what does all this mean?
Yeah.
Like, how does this randomness, this indeterminacy, change the way we see the universe?
Yeah, it's a big question.
It makes you wonder if we really have free will or if everything is just, predetermined.
That's a debate that's been going on for a long time.
Yeah, but I think this deep dive has shown us that the universe is way more complex and mysterious than we ever imagined.
Definitely.
And that even though there's randomness, there's also order and connection and maybe even purpose.
Yeah, there's still so much we don't know, but that's part of the beauty of it.
Right. The mystery keeps us exploring.
Exactly.
Well, on that note, I think we've reached the end of our deep dive into indeterminacy.
Time to resurface.
Yeah, but I have a feeling we'll be pondering these questions for a long time to come.
Oh, definitely.
Thanks for joining us on this journey, deep divers. We hope you've enjoyed exploring the bizarre world of randomness and indeterminacy with us.
And who knows what other mysteries we'll uncover in future deep dives.
Until next time, keep questioning, keep exploring, and